Hello! Welcome to Squid Essays. Inking your academic pen. My name is Julie and I will be your instructor as we read through radio packet position. The article source is embedded in the video description below. Feel free to read along. Please note that you can get a custom, plagiarism-free essay for as little as $10 a page at Squid Essays. The link is in the description. Abstract: This research demonstrates that the optimization for lower energy consumption leads to cross-layer design from the two ends, namely physical layer and the application layer. This optimization for quality of service requirements demands integration of multiple OSI layers. Open systems interconnect. Beginning from the physical layer, the probability of successful radio packet delivery is first explored. This probability, along with network energy consumption, is traded off to let CTPSN, Cooperative Transmission Protocol for Sensor Networks, demonstrate that sensor nodes' cooperative radio transmission exponentially reduces the outage probability when the node density increases. On the other hand, in MSSN, sensor networks with mobile sinks, the probability of successful information retrieval on the mobile sink is explored. Optimal and suboptimal transmission scheduling algorithms are then studied to exploit the trade-off between consumption and probability of successful radio packet delivery. In both the cases, optimizations lead to compound link layer and physical layer design. In the application layer, low-energy self-organizing protocols, LESOP, are studied for target tracking in dense wireless sensor networks. The application quality of service, COS, under study is the target tracking error in network energy consumption. A COS knob is utilized for controlling the trade-offs between target tracking errors and network energy consumption. Direct connections are found between the top application layer and bottom MAC, medium access control, / physical layers. Moreover, unlike the classical OSI paradigm of communication networks, transport and network layers are excluded in LESOP in order to simplify the protocol stack. The Embedded Wireless Interconnect, EWI, which has been proposed to replace the existing OSI paradigm as a potential universal architecture platform, is an effort towards standardization. EWI is built on two layers, which are wireless link layer and system layer, respectively. A brief study of EWI is also carried out. A network is a series of points or nodes interconnected by communication paths. Networks can interconnect with other networks and contain subnetworks. There are different types of networks. This chapter discusses briefly about ad hoc network, mobile ad hoc network, MANE, and wireless sensor networks, WSN, respectively. WNS is a wireless network consisting of spatially distributed autonomous devices using sensors to cooperatively monitor physical or environmental conditions at different locations. Sensor node deployment, power consumption, topological changes are some of the differences between WNS and MANE. There are various applications of wireless sensor networks, among which is target tracking. An ad hoc network is a sort of a temporary local area network or other small network. The network devices belong to the network only so long as there is some form of communication or information interchange within the network. The word ad hoc is derived from Latin. It literally means for a specific purpose and is therefore temporary. Ad hoc networks have several demerits, namely, an ad hoc network tends to feature a small group of devices all in very close proximity to each other. Performance suffers as the number of devices grows, and a large ad hoc network quickly becomes difficult to manage. Ad hoc networks cannot bridge to wirelands or to the internet without installing a special purpose gateway. The mobile ad hoc network, namely MANE, is well defined as an independent collection of many mobile users that can easily communicate in excess of relatively bandwidth-constrained wireless links. As the nodes are mobile, the network topology may vary unpredictably and rapidly over time. The network is decentralized, where the nodes themselves must execute all network movement together with delivering messages and discovering the topology, that is, routing functionality will be integrated into mobile nodes. Ranging from small, diverse, static networks that are controlled by power sources, to large-scale, highly dynamic networks, mobile are the applications for the MANEs. The main disadvantages of MANE are listed below. Regardless of the application, efficient distributed algorithms are needed by MANEs to determine link scheduling, routing and network organization. In a static network, the shortest path is based on a cost function given from a source to a destination is usually the optimal route. The idea disco sheet is not easily extended to mayonnaise. The design of the network protocols for these networks is a problematic issue. Factors such as propagation path loss, fading, variable wireless link quality, multi-user interference, topological changes and power expended become irrelevant issues. The word wireless network may exactly be used to refer to any kind of network that is wireless. The term is most commonly used to refer to a telecommunications network whose interconnections between nodes is implemented without the use of wires, such as a computer network. The different locations such as vibration, sound, temperature, motion, pollutants and pressure are monitored by using sensors of many, spatially distributed devices in a sensor network. The WSN, namely Wireless Sensor Network, is defined using sensors to look after environmental or physical conditions at various locations in a wireless network consisting of spatially distributed autonomous devices. WSNs differ in many fundamental ways from ANAs. Among the differences that may impact the network and protocol design are in a sensor network the number of sensor nodes can be several orders of magnitude higher than the nodes in an ad hoc network. Very frequently the topology of a sensor network changes vary. Sensor nodes are prone to failures. Sensor nodes are densely deployed. Communication paradigm is broadcasted using sensor nodes mainly, whereas most of the ad hoc networks are purely based on the point-to-point communications. Because of the large number of sensor and large amount of overhead, the sensor nodes may not have global identification, ID. Sensor nodes, are limited in memory, computational capacities and power. The following are the constraints of WSN, which have to be considering while developing an application in wireless sensor networks. Fault tolerance. Individual nodes are prone to unexpected failure with a much higher probability than other types of networks. The network should sustain information dissemination in spite of failures. Scalability, number in the order of hundreds or thousands. Protocols should be able to scale to such high degree and take advantage of the high density of such networks. Production costs, the cost of a single node must be low, much less than $1. Hardware constraints, a sensor node is comprised of many subunits: sensing, processing, communication, power, location, bonding system, power scavenging and mobilizer. All these units combined together must consume extremely low power and be contained within an extremely small volume. Sensor network topology must be maintained even with very high node densities. Environment. Nodes are operating in inaccessible locations either because of hostile environment or because they are embedded in a structure. Transmission media, RF, infrared and optical. Power consumption, power conservation and power management are primary design factors. In spite of the diverse applications, sensor networks pose a number of unique technical challenges due to the following factors: ad hoc deployment. Most sensor nodes are deployed in regions which have no infrastructure at all. A typical way of deployment in a forest would be tossing the sensor nodes from an airplane. In such a situation, it is up to the nodes to identify its connectivity and distribution. Unattended operation. In most cases, once deployed, sensor networks have no human intervention. Hence the nodes themselves are responsible for reconfiguration in case of any changes. Unethered, the sensor nodes are not connected to any energy source. There is only a finite source of energy, which must be optimally used for processing and communication. An interesting fact is that communication dominates processing and energy consumption. Thus, in order to make optimal use of energy, communication should be minimized as much as possible. Dynamic changes. It is required that a sensor network system be adaptable to changing connectivity, for example, due to addition of more nodes, failure of nodes etc., as well as changing environmental stimuli. Thus, unlike traditional networks, where the focus is on maximizing channel throughput or minimizing node deployment, the major consideration in a sensor network is to extend the system lifetime as well as the system robustness. Since many of the constraints of WNS are to deal with usage of sensor nodes, it's necessary to know about the sensors and sensor network architecture. Sensor network architecture. In a sensor field, the sensor nodes are usually scattered as shown in Figure 2.1. Each scattered sensor nodes has the capability to route data and collect data back to the sink. A sensor is a type of transducer. Sensor is a device that responds to a stimulus, such as light, pressure or heat, and generates a signal that can be interpreted or measured. A mode is the other name for it, that is capable of gathering sensory information, communicating with other connected nodes, and performing some processing in the network. A sensor node is made up of 4 basic components: a sensing unit, a processing unit, a transceiver unit. In addition to this may include components like a power generator, mobilizer, and location finding system. These components are known as application-dependent components. Generally, sensing units are typically collected of 2 subunits, ADCs, namely analog to digital converters, and sensors. ADC converts the analog signals created by the sensors based on the experiential fact to digital signals, and then fed into the processing unit. The storage unit is associated with the processing unit, and the measures are managed to make the sensor node collaborate with some extra nodes to bear out the allocated sensing tasks. A transceiver unit connects the node to the network. One of the most important components of a sensor node is the power unit. Power units may be supported by power scavenging units such as solar cells. There are also other subunits that are application dependent. Information of location with high accuracy is required by the majority of the sensing task and sensor network routing techniques. Hence, it is general that a sensor node has a location finding system. A mobilizer may sometimes be needed to move sensor nodes when it is required to carry out the assigned tasks. Sensor network protocol stack. This protocol stack combines routing awareness and power, communicates power competently through the wireless medium, integrates data with networking protocols, and promotes cooperative efforts of sensor nodes. The protocol stack consists of different layers such as the physical layer, data link layer, network layer, transport layer, application layer, mobility management plane, task management plane, and power management plane. The physical layer addresses the needs of simple but robust modulation, transmission, and receiving techniques. In view of the fact that the environment is noisy and sensor nodes can be mobile, the Medium Access Control (MAC) protocol must be power-aware and able to reduce impact with neighbors' broadcasts. The network layer takes a special to think about routing the data complete by means of the transport layer, and the transport layer helps the way to uphold the stream of data if the sensor network's application needed it. Dissimilar types of software can be built and used on the application layer depending on the sensing tasks. In addition, the power, mobility, and task management planes monitor the power, movement, and task distribution among the sensor nodes. These planes help the sensor nodes coordinate the sensing task and lower overall power consumption. While a sensor network's application, typical applications of WSNs include monitoring, tracking, and controlling. These specific applications are habitat monitoring, target tracking, nuclear reactor controlling, fire detection, traffic monitoring, environmental monitoring, acoustic detection, seismic detection, military surveillance, inventory tracking, medical monitoring, smart spaces, process monitoring, structural health monitoring, health monitoring. Among these applications, we will mainly study about target tracking in WSN. Target tracking is estimating the location of the target and then proceeding to find the path or track of the target. Sensor nodes in WSN monitor the movement of the target. Thus we see that though there are many kinds of networks like ad hoc network, many accuracy is higher in WNS. So with the help of the sensor nodes, target tracking can be done accurately using WNS. There are many different types of protocols and methods to perform target tracking, which will be discussed in next chapter. The LESOP protocol design will be discussed in 4th chapter. The implementation of the protocol and the end result will be discussed in the 5th chapter. The future enhancement and conclusion will be discussed in 6th chapter. Chapter: Literature Review. Target tracking is one of the applications of WNS. Many different method, protocol, and algorithm were adopted to detect and track the target. This chapter discusses briefly about the different algorithm, method, and protocol that were used to perform target tracking. They may include distributed online localization, cooperative tracking, collaborative target tracking, binary sensor model, building and managing aggregates, lightweight sensing and communication protocols, on linear measurement model, distributed state representation, optimizing tree reconfiguration, energy quality trade-offs, entropy-based sensor selection heuristic, an activity-based mobility model and trajectory prediction. Distributed online localization. A distributed online algorithm is used here. The sensor nodes put to use geometric constraints. These are induced by radio connectivity and sensors in order to minimize the uncertainty of their locations. In order to improve their and moving target positions, distributed online localization uses online observation of a moving target using sensor nodes. The nodes that act as reference nodes are pre-positioned into the network. The target is placed in an unknown position. Sensor nodes normally communicate with adjacent nodes. Size, ratio of known nodes, range of the radio and sensing range are taken into consideration when this algorithm is implemented. It has been verified that this algorithm can track targets with more accuracy over time by better estimation of nodes and target positions through sensor observations. When the ratios of reference nodes are high, his method can be applied to enhance position estimation accuracy. A binary detection sensor network is used in this area wherein the network sensor nodes can only establish if an object is within the maximum detection range. Information exchange between adjacent nodes refines location estimates, improving precision of tracking. This algorithm is in 2 levels. In level 1, local target position estimation is carried out. In the initial phase, the target is assumed to be equal to the position of sensor node. The position data is recalculated as weighted averages to sensor location when new information about the node is made available. Closer nodes get more weightage. These estimations are aggregated to obtain the path of the object. In level 2, a linear approximation of the path is calculated. This is done using the line-fitting algorithm on positions obtained in the previous level. The comparability of this approach to others such as distance measurements or angle of arrival measurements from sensors is confirmed by simulations. Because this approach puts to use binary detection sensors, it ends up being simpler and cheaper. Collaborative target tracking. This method is used to derive the effect of wireless network impairments on performance of the target tracking algorithm. It is applied in collaborative target tracking by using acoustic sensors. Target tracking by acoustic sensors demands multiple range or range estimation in order to carry out location estimation. Estimations are obtained by using a minimum of 3 range measurements. These are needed for a triangulation to precisely locate the target position. However, simultaneous range measurements are not possible as the target is mobile. Besides, over large networks, maintaining measurements is tricks. Some measurements may be dropped or get delayed. Accuracy suffers because of this. SCAAT Kalman filter is used to manage global time synchronization. The Kalman filter maintains a timestamp target state and updates the state when a single range or line of bearing is received. The digited buffer is used to store the received measured with a timeout. These buffer storages save a huge amount of unnecessary measurements. 2 types of nodes are found in this network. First type estimates the target's range angle. The second one, called fusion nodes, fuse the individual measurements. This results in a network without any packet loss or reordering. In more practical networks that suffer packet loss and reordering, the location error decreases as the buffering latency increases. Therefore, the de-jitter buffer helps save out-of-order packets. This model works on the assumption that each sensor in the network detects 1 bit of information, and this information is broadcast to the base station. This bit examines if an object is traveling away or towards the sensor. While this predicts the direction accurately, it does not yield the correct location. In order to do this, a particle filtering style algorithm is used for target tracking. Besides the 1-bit information, an additional bit is also gathered from proximity sensors to point out the exact location of the object. This tracking algorithm works on 3 assumptions, namely, sensors in a region can detect the target traveling towards or away from sensor. Bit information from every sensor is available in a central repository for processing, and finally, additional sensor supplies proximity information as a single bit is present. The error in trajectory prediction is rather low and the broadcast of a single bit over the whole network is easily feasible. The base station was also able to respond to the sensor values broadcasting at higher rates. This solution is very practical to simple tracking applications. Building and managing aggregates. This method introduces a decentralized protocol that constructs sensor aggregates in order to identify count distinct nodes or targets in the field. Sensor aggregates are nothing but nodes that satisfy group predicate. Task and resource requirements are the parameters for grouping predicate. These aggregates are used for performing a task in a collaborative manner. The DAM, Distributed Aggregate Management, protocol was introduced to support a representative and collaborative signal processing tasks. The DAM protocol forms many sensor aggregates in the sensor field. The following assumptions are made about the networks. Targets are single-point sources of signal. Sensors can mutually transfer information on the wireless within a fixed radius that is higher than the mean internode distance. Sensor times are synchronized to a global clock. And finally, that the battery power limits network bandwidth. Within a variation of parameters, this protocol has been observed to be effective in simulations. Lightweight sensing and communication protocols. There are quite a few lightweight sensing and protocols such as expectation maximization like activity monitoring, EMLAM, distributed aggregate management, DAM, and finally energy-based activity monitoring, EBAM. Protocol DAM was developed for target monitoring. Sensors used low-cost amplitude sensing. DAM carries out its purpose of electing local cluster leaders. The sensors in the network are classified into clusters on the basis of their signal strength, with each cluster having only one peak. Every peak represents a target as well as multiple targets that are close together. Each peak is identified by comparing heights of neighboring sensors. Sensor nodes exchange information to their one-hop neighbors. The cluster head leader is elected in the first phase as described above. Each sensor node is joined with a cluster that is defined by the highest peak that can reach that sensor through a path. Every leader can communicate with one or more targets in a defined period. DAM would not be capable to differentiate when there are many targets in a single cluster. To solve this problem, EBAM calculates the number of targets within each cluster. It also provides a solution to count targets within every sensor cluster made up by the DAM protocol. They assume each target has equal amounts of power. Since a single target is known, the number of target sensors in the cluster can be calculated from the total signal power calculated in the cluster. The third protocol, EMLAM, uses expectation maximization technique for intra-cluster target counting. It assumes targets are not clustered while entering the field. When moving together, sensor leaders will exchange information to track targets. The new target positions are estimated using a prediction model. Minimum mean square estimation, MMSE, is used for estimating location and target signal powers. Nonlinear measurement model. In the nonlinear measurement model, a particle filter approach is used for tracking targets in presence of spurious measurements, which provide information such as target wicks, multipath and tether decoys. In order to resolve the problem of intermittent measurements appearing behind the target, a measurement function is derived. The centroid of one of the sensors may be disturbed to point behind the actual target position due to environmental effects. This is called wake effect. This particular filter accommodates this bias and models a filter with discrete hidden Markov model. Simulation results show that intermittent corruptions of measurement process can still track a target using particle filtering. Distributed state representation. In this method, the state space model of physical phenomena is exploited. The dimension of the network increases with the presence and interaction of multiple targets. The issue of distributed sensing system to support monitoring in network has been dealt with in this method. Multiple target tracking is dealt with as an estimation problem. The position of target at time t is estimated using the state. Based on data collected, the actual location can be computed. Each target affects a local region of sensors in a distributed sensor network. In a multiple target neighborhood, the data will be shared across the network. Higher dimension tracking problem is broken into simple problems. Target states are decoupled into locations and identities. A joint estimation like centralized tracking approach is carried out when two targets move close to each other. While targets move away from each other, it will go back to single target tracking. However, sorting out the confusion of two targets will require identity management. Optimizing tree reconfiguration. This method focuses on energy-efficient detection and tracking mobile targets and introducing the concept of convoy tree-based collaboration, DCTC, whose framework is to track the target as it moves. Along with the target, the sensor nodes move around. The tree is reconfigured to add and remove nodes as the target moves. DCTC is an optimization problem that solves to find a convey sequence with the lowest energy consumption in two steps. The first level involves an interception-based reconfiguration algorithm that reconfigures the tree for energy efficiency. The next step is for route migration. Results demonstrate that this scheme has the lowest energy consumption. In this, we studied the energy-efficient trade-off of selective activation and random activation of the sensor nodes for tracking of mobile targets and localization. Based on trajectory prediction and duty-cycled activation, many approaches, namely randomized activation, selective activation and naive activation, are applied in this. The process described there gives the bang of deployment activation of sensor nodes, their capabilities of activated unactivated nodes, the target mobility model and their sensing range. While tracking, a good calculation in addition to a selective activation of algorithm provides more energy consumption, and it was been found in simulations. Moreover, better liveness and dynamic trade-off duty cycle activation displayed in energy expenses. Entropy-based sensor selection heuristic. This method proposes a novel entropy-based heuristic for sensor selection based on target localization. This involves selecting informative sensors in each tracking step, which is carried by using a greedy sensor selection strategy. This involves repeatedly selecting unused sensors with maximal expected information gain. Its purpose is to evaluate the expected information gain that can be attributed to each sensor. This should differ on average of the maximum entropy reduction of target location distribution. In developing this wireless network, the uncertainty in localization reduction attributable to a single sensor is primarily affected by entropy distribution of sensors' view on the location of the target and entropy of sensor sensing model for actual location. The heuristic is calculated by simulation to yield a reduction in the entropy while providing previous target location, its distribution, sensor locations, and sensing models. 13. All the methods discussed in this chapter uses OSI architecture, and the protocol stack has application layer, transport layer, network layer, data link layer and physical layer respectively. But the proposed LESOP protocol does not use OSI architecture but cross-layer architecture. Transport and network layer are being excluded in LESOP protocol stack. Chapter Design and Algorithm for High Protocol Efficiency. In LESOP, a perspective cross-layer design is adopted, where the direct relations between the medium access control (MAC) layer and application layer are exploited. Distinct the classical open systems interconnect (OSI) paradigm of communication networks. In order to simplify the protocol stack, the network layers and transport are excluded in LESOP. The lightweight, until now well-organized target localization algorithm is implemented and proposed, and the trade-off between the network energy consumption and the tracking error is found to control by a quality of service, QoS, knob. 3. This chapter discusses briefly about the modules and overall design of the LESOP protocol. The system module architecture of LESOP node is shown diagrammatically in Figure 3.1. The modules are named following the OSI tradition. The LESOP architecture virtually conforms to the proposed two-layer EWI platform. Inter-module information exchanges are done by messages and packets in busy tones to internode communications. Packets go through the primary radio, while busy tones are sent by the secondary wake-up radio. A set of inter-module messages, internode packets, tones, and module states for LESOP are defined. In wireless communications specifically, the transport and network layer are omitted to simplify the protocol stack. All the radio packets have one source address, which is the location coordinates LE of the source sensor node. They do not have a destination address, and are wirelessly broadcasted to the source neighborhood. In the LESOP design, the radio range is assumed to be 2 times larger than the sensing range. The assumption keeps the nodes set, that is, target detection nodes, within the range of each other. Application layer, APP, sensor, SEN, wake-up radio, WAR, MAC layer, MAC, physical layer, PHY. The role of the application layer is the overall control of the node functionalities. All the inter-node communications, packets or busy tones, start and end at the particular node application layer. It can be in one of the following four states: idle, wait, heady. Idle state. Initially all the deployed sensor nodes are in idle state. In this state, it is assumed that the target is undetected in the neighborhood region of the node. The application layer periodically pulls the sensor, sending SEN pull message, and read the sensing measurement, retrieving SEN measure message. The time period indicates how fast the target can be detected after appearing in the surveillance region. More specifically, the random variable denotes the detection delay, which is the time difference between the time the target appears and the first time that the target is detected. Once the target is detected, the application layer sends through the wake-up radio the busy tone BA, and transfers to HEADI state. BA forces all the neighboring sensor nodes become active. On the other hand, if BA arrives first, the application layer sends SEN PAL and transfers to wait state. Wait state. In wait state, the application layer first retrieves SEN measure message from the sensor. If the sensed measurement greater than the threshold measurement, it returns to idle state at the end of the track interval. Otherwise, the detection coefficient is calculated locally and included in the DEC info packet and forwarded to the MAC layer. The first busy tone BB indicates that the leader node H2 has been elected in the neighborhood. When the DEC ready message is received from the MAC layer, this specific node becomes H2, if H2 has not been elected. Correspondingly, the application layer transfers to heady state, and sends DEC cancel message to the MAC layer to cancel the current DEC info packet. If it is known that H2 has been elected upon receiving DEC ready, the application layer replies to the MAC layer with a confirmation DEC set message. The second busy tone BB indicates that the target location estimation procedure has ended. When it arrives, the application layer sends DEC cancel message to the MAC layer, and transfers to idle state. HEADI state. In HEADI state, the node behaves as the H1 node. The application layer waits for the second busy tone BB from the wake-up radio. As the desired BB arrives, it sends track info packet through the primary radio, and waits for the acknowledgement, track app packet, from H2 node. After the exchange, the application layer goes to the idle state. If the second BB does not arrive within the track interval limit, the node decides that the target has disappeared or errors have occurred. Application layer transfers to idle state, and the track record is then forwarded to the sync by other mechanisms. Heady state. In heady state, the node behaves as the H2 node. First, BB busy tone is broadcasted through the wake-up radio, which announces that H2 has been elected. Radio ACT message is then sent to set the physical layer in receive idle state, turning on primary radio. The application layer receives DEC info packets from the neighborhood in sequence. The detection information fusion process is then executed as described in LESOP protocol algorithm. Once the terminating condition is met, that is determining optimal number of nodes, or the track interval time limit is reached, the target location is estimated by optimal linear combing method. The second BB is then broadcasted through the wake-up radio, indicating that the estimation procedure has finished. After the broadcasting of the second BB, the application layer waits for track info packet from H1, and responds with the acknowledge, track app packet. The application layer then sends a radio SLE message to set the physical layer in sleep state, turning off primary radio. When the track interval time is reached, BA is broadcasted through the wake-up radio and the application layer transfers to HEADI state. The MAC layer receives the DEC info packet from the application layer. It calculates a time delay for the DEC info packet. It waits until the expiration of the time delay to perform radio carrier sensing. If the primary radio channel is busy, the MAC layer waits for another time delay, which is the DEC info packet transmission delay. When the radio channel is free, DEC ready is sent to the application layer. If the response is DEC set, the deck info packet is forwarded to physical layer and broadcasted. Else, if the application layer response is deck cancel, the deck info packet is deleted in MAC. At any time when deck cancel message is received, the current deck info packet waiting in the buffer is deleted. After receiving track info or track ACK packets from the application layer, the MAC performs radio carrier sensing and waits until the radio channel is free. The track info or track ACK packets are then forwarded to the physical layer and broadcasted. The MAC layer also forwards all the received packets from the physical layer to the application layer. A collision of deck info packets can occur when the difference between the MAC time delays of two nodes is less than the range of their radios. Since range is small in sensor networks, the collision probability is practically small. The LESOP protocol is virtually robust to the collision, since H2 can ignore the collision and wait for the next successfully received deck info packet. The Channel Error Control Coding (ECC) functionality is added to the MAC layer. Traditionally, ECC is defined at data link layer, and MAC is a sub-layer of data link layer. It provides us with an efficient wave presentation. The physical layer of primary radio is responsible for broadcasting the radio packets to the node's neighborhood, which in our simplified model is a circular region with radius as range of radios. It also supplements carrier sensing capability to MAC layer and detects radio packets collision on primary radio. The physical layer can be in one of the three states: transmit, receive idle, and sleep, which correspond to the three modes of primary radio: transmitting, receiving idle, and sleeping, respectively. When receiving the forwarded packets from the MAC layer, the physical layer goes to transmit state and returns to the previous state after transmission. The application layer configures the physical layer in receive idle or sleep states by radio ACT or radio SLE messages, respectively. The wake-up radio and the sensor modules are under control of the application layer. Wake-up radio broadcasts the busy tone forwarded from the application layer and sends the detected busy tone to the application layer. After receiving SE PAL message from application layer, the sensor module is activated, senses and responds the sensing measurement by sending SE measure message. 1. High-level LESOP protocol description: a low-complexity processing algorithm for target tracking, which is based on the sensor measurements, is assumed. The high-level LESOP protocol description, which is an iterative procedure, the process is described below. The node distribution can be modeled as Poisson process. The node that first detects the target is considered as first leader node. The neighboring nodes are selected based on following two conditions: sensing measurement of sensor node, detection threshold of sensor node, distance between leader node and sensor node, range of radios. Node deployment: electing leader NODE1, determine neighboring nodes, calculate fusion detection company efficiency at every node, electing leader NODE2, determining optimized set of nodes, determining estimated target company ordinates. Leader NODE1 sends track info to leader NODE2, new track info by leader NODE2, LEADER NODE2 ACTSS LEADER NODE1 loop. The fusion detection company efficient are calculated using the following parameters: sensing measurement of sensor node, sensing gain of sensor node. The node with highest fusion detection company efficient is elected as next leader node. The detection information fusion is done at this newly elected leader node. A selected number of nodes from a node set that have detected the target participate in the fusion by sending the detection information to newly elected node. The nodes participating in the detection fusion are determined based on the improvement ratio of accuracy calculated for set of nodes, which is given as min value fusion detection coefficient, sum of all fusion detection coefficients. The estimated target coordinates are calculated using optimal linear combining. The leader node 1 sends the old track information to leader node 2, which includes a profile of target. The leader node 2 generates the new track information. This continues until the target is tracked. Project flow: sets is as a first leader node. H1 sends wake-up message 1 to RF channel. RF channel sends wake-up message 1 to all nodes. The next leader node is elected, H2, and the next leader sends wake-up message 1. RFC transmits wake-up message 2 to all nodes. Target estimation procedure is completed once the message 2 has been sent. The first leader node, H1, sends the track information to the funnel to be transmitted to the H2, H2 sends the track information acknowledgement to RFC, which then sends to leader node. H2 now acts as the H1 and sends the wake up MSG1 to all other nodes through RFC. The next leader node is elected and the procedure is continued until the target moves out of range. The energy consumed by the sensor nodes remains constant at certain period of time. Though the number of nodes increases, the network energy consumption is maintained constant. An LESOP protocol is proposed for target tracking in wireless sensor networks, based on a holistic cross-layer design perspective. Linear processing is employed for target location estimation. Compared with the optimal nonlinear estimation, the proposed linear processing achieves significantly lower complexity, which makes it suitable for sensor networks implementation. A CoS-NOP coefficient is found in optimizing the fundamental trade-off. Moreover, the protocol is fully scalable because the fusion coefficient is calculated locally on individual sensor nodes. In the protocol design of LESOP, direct interactions between the top application layer and the bottom MAC physical layers are exploited. The traditional network layer and transport layer have been removed, thus simplifying the protocol stack. Some traditional functionality of the two layers is merged into the top and the bottom layers. This chapter discusses the implementation of modules and end result. The implementation is performed in simulation software, OMT++. OMT++ is a public source, component-based, modular and open architecture simulation environment with strong GUI support and an embeddable simulation kernel. It requires Microsoft Visual C++. It can be installed both in Windows and Linux. The version 3.0 is used in this project. Its primary application area is the simulation of communication networks, and because of its generic and flexible architecture, it has been successfully used in other areas like the simulation of IT systems, queuing networks, hardware architectures and business processes as well. To implement your first simulation from scratch, we need to follow the following steps. 1. The working directory is created, it's called as TicTac, and the CD to this directory. 2. By creating a topology file, the example network is described. The network's nodes and the links between them can be identified by a topology file, which is in the form of text file. You can generate it with your preferred text editor. Let's call it TikTok1net. The file is finest to read from the bottom up. Here's what it defines. A network called TikTok1 is defined, which is an instance the module type TikTok1, network endwork. TikTok1 is assembled from two submodules, which is Tik and Tok, and it's a compound module. The two submodules, Tik and Tok, are instances of the identical module type called TXC1. The Tik's output gate, which is named as out, is connected to Tok's input gate, which is named as in, and vice versa, module and module. In both ways there will be a 100 milliseconds propagation delay. TXC1 is atomic on any D level, and it will be implemented in C++. So TXC1 is known as a simple module type. TXC1 has one input gate and one output gate, which is named as an and out respectively, simple and simple. 3. By writing a C++ file TXC1cc, we can achieve the implementation of the functionality of the simple module TXC1. The C++ class TXC1 represents the TXC1 simple module type, which has to be registered in OMT++ with the defined module macro and subclassed from C simple module. The two methods is redefined from C simple module, handle message and initialize. From the simulation kernel they are invoked, the first one only once, and the second one whenever a module receives the messages. A message object, CMessage, is created in initialize, and drive it out via gate out. From the time when this gate is linked to the other module's input gate, after a 100 milliseconds propagation delay assigned to the link in the NED file, the simulation kernel will convey this message to the other module in the dispute to handle message. It will result in continuous ping-pong because the other module just sends it back, another 100 milliseconds delay. Message objects, or its subclass, represent the events, timers, timeouts, and messages, packets, frames, jobs, etc. in OMT++. Later then you send or schedule them, They will be held by the simulation kernel in the future events or scheduled events list in anticipation of their time comes, and they are delivered to the modules using handle message. We have to note that there is no stopping condition built into the simulation. It would carry on forever. From the GUI we will be able to stop it. 4. The compile and link our program to generate the executable TikToks done with the help of creating the makefile. In the working directory TikTok, makefile is now created with the help of this command. Note: Windows plus MSVC users, to create a makefile VC, the command is op-make. 5. Now link our very first simulation by issuing the make command and compile. Note: lines beginning with our comments parameters TikTok for talk limit equals 5 argument to exponential is the mean. Trunc normal returns values from the normal distribution truncated to non-negative values. TikTok 6 tick delay time equals exponential. 3. TikTok 6 talk delay time equals trunc normal. 3. 1. TikTok 9n equals 5 TikTok 10n equals 5 TikTok 11n equals 5. The simulation program asks, which even doesn't specify the network in a dialog when it starts. 7. After completing the above commands, by delivering this command you can open the simulation and hopefully you will get the OMT++ simulation window. Note: Windows, the command we are used is just TikTok. 8. The simulation is started by pressing the Run button on the toolbar. The simulated time is displayed in the main window toolbar displays. This is known as virtual time. It can't do anything with the wall clock or actual time that the program takes to perform. The speed of your hardware and even more on the nature and complexity of the simulation model itself determines how many seconds you can simulate one real-world second. Note that the time taken for a node to process the message is 0 simulation time. The propagation delay on the connections is the only thing that makes the simulation time pass in this model. 9. We can run by making it quicker with the slider at the top of the graphics window or with slowing down the animation. The simulation can be stopped by hitting F8, equivalent to the STOP button on the toolbar. F4 is used to single step through it, F5 used to run it with, or F6 is for without animation. F7 is for express mode, which are fully turns off tracing features for maximum speed. Note the event sec and simsec gauges on the status bar of the main window. 10. By choosing File Exit or clicking its close icon you can exit the simulation program. 8. To generate the makefile in the OMNet++ 3.0 environment the following command is being used, %op-make. Using the following command the object files for all the CPP files are generated and it also generates the executable file for running the simulation network, %make-f makefile VC. The executable file is run which generates the simulation network. Various steps are included in the working. Step 1. The node that first detects the target is considered as first leader node. The node 31 sends wake-up message 1 to the refanel. Step 2. The wake-up message 1 is transmitted to all the other nodes. This is done through refanel. Figure 4-2 RFC transmits wake-up MSGL to all other nodes. Step 3. The next leader node is elected. The node 17 sends wake-up message 1 to the refanel. Step 4. The first wake-up message 2 is transmitted to all the other nodes to indicate that the leader node 2 has been elected. Figure 4-4 RFC transmits wake-up MSG2 to all other nodes. Step 5. The second wake-up message 2 is transmitted to the refanel from sensor node 17, once it finishes the target location estimation procedure. Step 6. The second wake-up message 2 is transmitted to all the other nodes through refanel. Step 7. The sensor node 31, H1 sends the track information to the refanel to be transmitted to the H2 which is sensor node 17. Step 8. The sensor node 17, H2 sends the track information acknowledgement to RFC which then sends to leader node H1, sensor node 31. Step 9. The sensor node 17 now acts as the H1 and sends the wake-up MSG1 to all other nodes through RFC. Step 10. The next leader node is elected and the procedure is continued until the target moves out of range. Step 11. The energy consumed by the sensor nodes remains constant at certain period of time. Though the number of nodes increases, the network energy consumption is maintained constant. The A9AYTZ 3.0 is being implemented in Windows XP to generate the simulation environment. C++ programming language is being used and the desired output is examined. The sensor network is created with 80 nodes and the corresponding messages are transferred between the nodes. The vector graph is generated once the simulation ends. The conclusion and future enhancements are described in the 5th chapter. Chapter: Conclusion and Future Enhancements. This chapter discusses the future enhancements and the conclusion of the target tracking in wireless sensor network. The idea behind sensor networks cross-layer design is to optimize the basic trade-off in sensor networks, the trade-off between application-specific OS gain and energy consumption expenditure. As of now, cross-layer optimizations need to be done in a holistic manner as research communities are trying to reach an acceptable new architecture. However, the holism may not necessarily be affordable in the future. As complexities in the networks grow, it is the hierarchical layers provide long-term efficiency and propagation. The alteration on layer of protocol stacks does not require the rewriting of entire protocol stack. This dissertation research rests heavily on an organized study of the sensor network's cross-layer design. The first chapter discusses the overall description of the project and the area in which the project is carried out. The different types of protocols and methods used to perform target tracking are explained in Chapter 2. The LESOP protocol design has been discussed in the 3rd chapter along with algorithm of each module. The implementation of the protocol and the end result has been discussed in the 4th chapter. Future enhancements in wireless sensor networks are seen in Embedded Wireless Interconnect, EWI, area. The EWI is used for replacing the existing OSI structures. It is built on 2 layers which are system layer and wireless link layer respectively. The experimental and theoretical background studies lead to an explanation of the general interface syntax between the 2 layers and suggests that the separate dealing of source and channel coding in wireless link layer and system layer can achieve optimal twist and energy consumption trade-off and reach far wireless sensor networks, asymptotically. The main module includes sub-modules of application layer, MAC layer, physical layer, sensor, recorder and the target. MAC module interface, sensor host MAC, parameters, parameter, TX rate, part type numeric part type const, parameter, TD max, part type numeric part type const, gates, gate, to PHY, gate ear output, gate, to app, gate ear output, gate, from app, gate ear input, gate, from PHY, gate ear input, end interface register module interface, sensor host MAC, APP module interface, sensor host app, parameters, parameter, location X, part type numeric part type const, parameter, location Y, part type numeric part type const, parameter, lambda app, part type numeric part type const, parameter, December interval, part type numeric part type const, parameter, mic noise, part type numeric part type const, parameter, DETPK len, part type numeric part type const, parameter, mic sample, part type numeric part type const, parameter, sensing interval, part type numeric part type const, parameter, decay component, part type numeric part type const, parameter, track PK len, part type numeric part type const, parameter, ACK PK len, part type numeric part type const, gates, gate, to MAC, gate ear output, gate, to send, gate ear output, gate, from MAC, gate ear input, gate, from send, gate ear input, end interface register module interface, sensor host app, channel module interface, wireless channel, parameters, parameter, decay component, part type numeric part type const, parameter, shadowing, part type numeric, parameter, number host, part type numeric part type const, parameter, propagation delay, part type numeric part type const, parameter, RF range, part type numeric part type const, gates, gate, in, gate ear input, end interface register module interface, wireless channel, recorder module interface, system recorder, parameters, parameter, number host, part type numeric part type const, parameter, interval, part type numeric part type const, gates, gate, in, gate ear input, end interface register module interface, system recorder, target module interface, target location, parameters, parameter, energy, part type numeric, parameter, decay component, port type numeric bar type const, parameter, number host, port type numeric bar type const, parameter, interval, port type numeric bar type const, parameter, max v, port type numeric bar type const, parameter, send range, port type numeric bar type const, parameter, range, port type numeric bar type const, parameter, propagation delay, port type numeric bar type const, parameter, enter time, port type numeric bar type const, parameter, leave time, port type numeric bar type const, end interface register module interface, target location, physical module interface, sensor host phi, parameters, parameter, ref noise, port type numeric bar type const, parameter, ref power, port type numeric bar type const, parameter, p activate, port type numeric bar type const, parameter, p transmit, port type numeric bar type const, parameter, threshold, port type numeric bar type const, gates, gate, from Mac, gate dear input, gate, RFIN, gate dear input, gate, to Mac, gate dear output, end interface register module interface, sensor host phi, sensor module interface, sensor, parameters, parameter, mic noise, port type numeric bar type const, parameter, mic sample, port type numeric bar type const, parameter, ESCN, port type numeric bar type const, gates, gate, SENIN, gate dear input, gate, from app, gate dear input, gate, to app, gate dear output, end interface register module interface, sensor, submodule Mac markup equals get module type, sensor host Mac. C module Mac P equals markup create, Mac, mod. Int Mac size equals 1. Parameter assignments, Mac P par, TX rate equals mod par, TX rate. Mac P par, TD max equals mod par, TD max. Read module parameters, Mac P. Submodule app markup equals get module type, sensor host app. C module app P equals markup create, app, mod. Int app size equals 1. Parameter assignments, app P par, location X equals mod par, location X. App P par, location Y equals mod par, location Y. App P par, mic noise equals mod par, mic noise. App P par, mic sample equals mod par, mic sample. App P par, DETPK len equals mod par, DETPK len. App P par, track PK len equals mod par, track PK len. App P par, ACK PK len equals mod par, ACK PK len. App P par, sensing interval equals mod par, sensing interval. App P par, decay component equals mod par, decay component. App P par, lambda app equals mod par, lambda app. App P par, December interval equals mod par, December interval. Read module parameters, app P. Submodule send markup equals get module type, sensor. C module send P equals markup create, sen, mod. Int send size equals 1. Parameter assignments, send P par, mic noise equals mod par, mic noise. Send P par, mic sample equals mod par, mic sample. Send P par, ESCN equals TMPVAL set double value, new EXPRO, mod. Read module parameters, send P. Submodule phi markup equals get module type, sensor host phi. C module phi P equals markup create, phi, mod. Int phi size equals 1. Parameter assignments, phi P par, ref noise equals mod par, ref noise. Phi P par, ref power equals mod par, ref power. Phi P par, threshold equals mod par, RFTHRESHOLD. Phi P par, P activate equals mod par, P activate. Phi P par, P transmit equals mod par, P transmit. Read module parameters, phi P. Submodule bat markup equals get module type, battery. C module bat P equals markup create, bat, mod. Int bat size equals 1. Parameter assignments, bat P par, energy lev ini equals mod par, energy lev ini. Read module parameters, bat P. Connections, C gate trick gate, desk gate. C channel channel. C par par. Connection trick gate equals check gate, phi P, to Mac. Dest gate equals check gate, MAC P, from Phi. Switch gate connect to, Dest gate. Connection switch gate equals check gate, send P, to app. Dest gate equals check gate, app P, from sen. Switch gate connect to, Dest gate. Connection switch gate equals check gate, MAC P, to Phi. Dest gate equals check gate, Phi P, from MAC. Switch gate connect to, Dest gate. Connection switch gate equals check gate, app P, to sen. Dest gate equals check gate, send P, from app. Switch gate connect to, Dest gate. Connection switch gate equals check gate, MAC P, to app. Dest gate equals check gate, app P, from MAC. Switch gate connect to, Dest gate. Connection switch gate equals check gate, app P, to MAC. Dest gate equals check gate, MAC P, from app. Switch gate connect to, Dest gate. Connection switch gate equals check gate, mod, sen in. Dest gate equals check gate, send P, sen in. Switch gate connect to, Dest gate. Connection switch gate equals check gate, mod, RFIN. Dest gate equals check gate, Phi P, RFIN. Switch gate connect to, Dest gate. This level is done. Recursively build submodules to MAC P build inside. App P build inside. Send P build inside. Phi P build inside. BAT P build inside. Submodule target mod equals get module type, target location. C module target P equals mod create, target, mod. In target size equals 1. Parameter assignments, target P par, energy equals TMPVAL set double value, new EXPR1, mod. Target P par, number host equals mod par, number host. Target P par, propagation delay equals mod par, a propagation delay. Target P par, interval equals mod par, sen interval. Target P par, max V equals mod par, max V. Target P par, sen range equals mod par, sen range. Target P par, range equals mod par, range square. Target P par, decay component equals mod par, a decay component. Target P par, enter time equals mod par, target enter time. Target P par, leave time equals mod par, target leave time. Read module parameters, target P. Submodule recorder mod equals get module type, system recorder. C module recorder P equals mod create, recorder, mod. Int recorder size equals 1. Parameter assignments, recorder P par, number host equals mod par, number host. Recorder P par, interval equals mod par, record interval. Read module parameters, recorder P. Submodule refanel mod equals get module type, wireless channel. C module refanel P equals mod create, refanel, mod. Int refanel size equals 1. Parameter assignments, refanel P par, decay component equals mod par, decay component. Refanel P par, shadowing equals TMPVAL set double value, new EXPR2, mod. Refanel P par, number host equals mod par, number host. Refanel P par, RF range equals mod par, RF range. Refanel P par, propagation delay equals mod par, propagation delay. Read module parameters, refanel P. Submodule sensors mod equals get module type, sensor host. Int sensor size equals, int, mod par, number host. Check module vector size, sensor size, sensors. C module sensors P equals new C module sensor size. 4. Submode index equals 0. Submode index sensor size. Submode index plus sensors P submode index equals mod create, sensors, mod, sensor size, submode index. Parameter assignments, sensors P submode index par, TX rate equals mod par, RRF. Sensors P submode index par, energy lev ini equals mod par, energy lev ini. Sensors P submode index par, DETPK line equals mod par, LD. Sensors P submode index par, track PK line equals mod par, LT. Sensors P submode index par, ACK PK line equals mod par, LA. Census piece submode index par, ref noise equals mod par, ref noise. Census piece submode index par, mic noise equals mod par, sigma I2. Census piece submode index par, ref power equals mod par, ref power. Census piece submode index par, RFTHRESHOLD equals mod par, RFTHRESHOLD. Census piece submode index par, mic sample equals mod par, sen n. Census piece submode index par, p activate equals mod par, p activate. Census piece submode index par, p transmit equals mod par, p transmit. Census piece submode index par, location x equals tmpval set double value, new expr3, mod. Census piece submode index par, location y equals tmpval set double value, new expr4, mod. Census piece submode index par, psen equals mod par, psen. Census piece submode index par, td max equals mod par, td max. Census piece submode index par, lambda app equals tmpval set double value, new expr5, mod. Census piece submode index par, sensing interval equals mod par, tsen. Census piece submode index par, December interval equals mod par, ttrack. Census piece submode index par, decay component equals mod par, a decay component. Census piece submode index par, sensor fs equals mod par, sensor fs. Read module parameters, census piece submode index. This level is done, recursively build submodules to target p build inside. Recorder p build inside. Refiddle p build inside. 4. Submode index equals 0. Submode index sensor size. Submode index plus sensors p submode index build inside. Delete sensors p. There are several packets, messages, and busy tones that get transferred between the nodes for every event. The definition and specification of the packets include various attributes. The ref packet includes the following data: tx rate, transmission rate, sending power, transmitting power, receiving power, location xx coordinate, location yy coordinate. The deck info packet includes the following data: data fusion company efficient. The track info packet includes the following data: track xx coordinate, track yy coordinate, record time of recording, true x original x coordinate, true y original y coordinate. The above message packets are transmitted between the nodes during corresponding events. For example, consider that the sensor node 17H1 sends the track information to node 3H2. The track info packet resembles as given below. Node 17 sending track info to node 3 double tx rate equals 20,000,000,000 double, sending power equals 1.0000000 double, receiving power equals 0.048157 double, location x equals 16.652397 double, location y equals 19.143103 and number equals 1 double, track x equals 15.996901 double, track y equals 18.05 9343 and NCOUNT equals 3. Double, record time equals 30.899702 double, true x equals 14.933409 double, true y equals 18.713991. Similarly, the packet includes various different information depending on the type of packet sent received. W.B. Heinzelman and A.P. Chandrakishan, an application-specific protocol architecture for wireless microsensor networks, IEEE Trans. Wireless Common, Volume 1, page 660, October 2002. X. Sheng and Y. Hu. Maximum likelihood multiple source localization using acoustic energy measurements with wireless sensor networks, IEEE Trans. Signal Process, Volume 53, page 44, January 2005. Liang Song, A cross-layer architecture of wireless sensor networks for target tracking, IEEE ACM Transaction on Networking, TON, Volume 15, Issue 1, page 145 to 158, February 2007. OMNET++ Manual, http://www.omnet.org/ List archive /MSG101111.php Balakrishnan, K. Jameson NYC TASIFT, a MAC protocol for event-driven wireless sensor networks, Published on 2003. A9AYTZ, W. Su, Y. Subramaniam and E. Karachia Survey on Sensor Networks, IEEE Common. Mag. Page 102, August 2002. J. Moore, R. Brooks, T. Kaiser, S. Fua, J. Koch, D. Friedlander, A. Reggio and N. Jacobson. Tracking targets with self-organizing distributed ground sensors, Proc. IEEE Arrays Base Conf. Page 5-2113, 2003. OMT++ tutorial, available online, http://www.omt.org/ doc/ TikTok-tutorial/ Part 1.html GUI and PMOA Power Conservation and Quality of Surveillance in Target Tracking Sensor Networks, Proc. ACM Mobicom, page 129, 2004. W.E. J. Heitman and D. S. Train an Energy-Efficient MAC Protocol for Wireless Sensor Networks, Proc. IEEE Infocom, page 1567, 2002. Sequo, L.C. Zhang and J. M. Rabari. Low Power Distributed MAC for Ad Hoc Sensor Radio Networks, Proc. IEEE Globcom, page 2944, 2001. S. Haken Array Signal Processing Englewood Cliffs, N.J., Prentice Hall, 1985. Target Tracking Literatures, http://networks.cs.ugvis.etches/ /. Research/ Target Tracking Summary.html. Segrestrin, P. Bodict, Art Thibault, M. Paskin and S. Madden. Distributed Regression, an efficient framework for modeling sensor network data, Proc. 3rd ed. SIMP. Information Processing in Sensor Networks, IPSN 2004, page 1, April 2004. D. Lee, K. Wang, Y. Hu and A. Saoyi. Detection, Classification, and Tracking of Targets, IEEE Signal Process. Mag. Volume 19, page 17, March 2002. V. Kawadia and Pierre Kumar. Cautionary Perspective on Cross-Layer Design, IEEE Wireless Common. Mag. Volume 12, page 3, February 2005. Waizu and K. Chakrabarty. Target Localization Based on Energy Considerations in Distributed Sensor Networks, Proc. First IEEE Workshop on Sensor Network Protocols and Applications, SNPA 2003, page 51, May 2003. Liang Song and D. Hatsunako's Energy Efficiency Limits of Broadcasting in Wireless Networks, IEEE Trans. Wireless Communications, May 2005. R. Brooks, P. Ramanathan and A. Saoyi. Distributed Target Classification and Tracking in Sensor Networks, Proc. IEEE, Volume 91, page 1163, August 2003. T. Dam and K. Long and an Adaptive Energy Efficient MAC Protocol for Wireless Sensor Networks, Proc. ACM 1st ed. Conf. Embedded Network Sensor Systems, Census 03, page 171, November 2003. T. He, J. A. Stankovic, C. Lu and T. Abdulzar. Speed, a stateless protocol for real-time communication in sensor networks, Proc. Int. Conf. Distributed Computing Systems, ICDCS, 2003, page 46, 2003. H. Gupta, S. Das and Q. Connected Sensor Cover, Self-Organization of Sensor Networks for Efficient Query Execution, Proc. Mobyhawk, page 189, 2003. J. G. Prowakis. Digital Communication, 3rd edition. New York, McGraw-Hill, 1995. X. Wang, G. Crossing, Y. Zheng, C. Lu, R+, and C. Jill. Integrated Coverage and Connectivity Configuration in Wireless Sensor Networks, Proc. ACM 1st ed. Conf. Embedded Network Sensor Systems, Census, Los Angeles, California, page 28, 2003. Essing and C.S. Raghavendra PAMAS, Power-Aware Multi-Access Protocol with Signaling for Ad Hoc Networks, ACM Compute. Common. Rev. Volume 28, page 5, July 1998. P. Venkata Subramaniam, S. Addereti and L. Tong Opportunistic Aloha and Cross-Layer Design for Sensor Networks, Proc. IEEE Military Common. Conf. Page 705, October 2003. C. Shirkers, A9AYTZ358T, Escamerwal and M. Srivastava Optimizing Sensor Networks in the Energy Latency Density Design Space, IEEE Trans. Mobile Compute, Volume 1, page 70, January-March 2002. W. Zhang and G. Cao Optimizing Tree Reconfiguration for Mobile Target Tracking in Sensor Networks, Proc. IEEE Infocom, page 2434, 2004. F. Xiao, J. Shin and J. Reich Information-Driven Dynamic Sensor Collaboration, IEEE Signal Process. Mag, Volume 19, page 61, March 2002. Scaglione and Y.W. Wong Opportunistic Large Arrays, Cooperative Transmission in Wireless Multi-Hop Ad Hoc Networks to Reach Far Distances, IEEE Trans. Signal Process, Volume 51, page 2082, August 2003. IEEE Trans. Acoust, Speech, Signal Process, Special Issue on Time Delay Estimations, Vol. ASSP 29, January 1981. Thank you for taking your time to listen to me. I hope you enjoyed learning about radio packet position as much as I did. Kindly remember that you can get a custom, plagiarism-free essay at Squid Essays for as little as $10. The link is in the description. See you next time.